In this video, we're going to cover parametric curves, first and second derivatives and their applications, and then also for parametric curves, we're going to do arc length. First, we have a note. It says a parametric curve x of t, y of t is differentiable at t if x and y are differentiable at t. At a point on a differentiable parametric curve where y is also a differentiable function of x, the derivatives dy dt, dx dt, and dy dx are related by the chain rule. So here we have dy dt equals dy dx times dx dt. Next it says if dx dt is not equal to 0, we can divide both sides of this equation up here by dx dt, and that will let us solve for dy dx. So right here's your dy dx. When we divide both sides by this dx dt, then it will give us our expression for dy dx, which is our slope. Next, it says by doing so, it enables us to find tangents to parametric curves without having to eliminate the parameter. Next, it says by doing so, it enables us to find tangents to parametric curves without having to eliminate the parameter, so we can still find dy dx. So that leads us into our definition for dy dx for a parametric curve. Dy dx is equal to dy dt divided by dx dt. And again, this is permitted that dx dt doesn't equal 0. A parametric curve has a horizontal tangent when the numerator is equal to 0, so that's dy dt equals 0. And again, it's still with the condition that this denominator doesn't equal 0. And a parametric curve has a vertical tangent when the denominator is equal to 0 or dx dt equals 0. Our next definition is a second derivative for a parametric curve. Again, this is Leibniz's notation for a second derivative, d2y over dx squared. Our formula for a second derivative of a parametric curve is this right here, so I would definitely highlight this or box it. To find the second derivative, you take the first derivative, dy dx, and you take the derivative of it with respect to t, and then finally you take that expression and divide it by dx dt. Next, it says we already know how to find the length L of a curve C given in the form y equals f of x from a to b. If f prime is continuous on the closed interval from a to b, then we have this formula for length of a curve. It's the integral from a to b of the square root of 1 plus dy dx squared. And next we have a formula for the length of a parametric curve that's given in the form x of t, y of t. So if t is between alpha and beta, to find the length, it's the integral from alpha to beta of the square root of dx dt squared plus dy dt squared. This example says find an equation of the tangent to the curve at the point corresponding to the given value of the parameter. So we have that x equals 2t squared plus 1 and y equals 1/3 t cubed minus t, and then our parameter t is equal to 3. So to write the equation of a tangent line to the curve, even though this is a parametric equation, we still use the same process. We need point and slope. So first I'm going to take the derivative of x with respect to t and then also the derivative of y with respect to t. So dx dt, we take the derivative of this right here. The derivative of 2t squared is going to be 4t, and the derivative of 1 is 0. Next, we're going to find dy dt. So dy dt is t squared minus 1. So now that we have dx dt and dy dt, we're going to find slope. So slope is dy dx, and for parametric equations, dy dx is equal to dy dt over dx dt. So what we do is we take this dy dt and we put that expression in the numerator, and then we put this expression for dx dt in the denominator. So we get that slope is t squared minus 1 over 4t, and now we're going to plug in t equals 3. So we're going to take this 3 and plug it in for t here and here. So in the numerator we get 9 minus 1 is 8, and then in the denominator we get 12, and that reduces to 2/3. Next, we're going to find the point, so we're going to take t equals 3 and we'll plug it in here and here to find x and y. All right, so we have x equals 2 times 3 squared plus 1, and we have y equals 1/3 3 cubed minus 3. So over here, 3 squared is 9, 9 times 2 is 18, and 18 plus 1 is 19. And then right here we have 3 cubed divided by 3 is going to make 9, and 9 minus 3 is 6. All right, guys, we have slope is 2/3, and then the coordinate point is 19,6. So we're going to plug those into point slope form to get the equation of a tangent line. And we get y minus 6 equals 2/3 times the quantity x minus 19. This example says find an equation of the tangent to the curve at the given point by first eliminating the parameter. We have x equals tangent of theta and y equals secant of theta, and then we have the coordinate point 1 comma root 2. So again, for the equation of a tangent to a curve, we need point and slope, and I just wrote that we already have a point, so we already have 1 comma root 2, so now we just need slope. So to find the slope, we're going to use the Pythagorean trig identity, secant squared equals 1 plus tangent squared. Since y equals secant, we're going to plug in y right here, so we're going to get y squared. And since x equals tangent, we're going to plug in x right here to get x squared. Next, to find our slope, which is dy dx, we're going to differentiate implicitly with respect to x. So the derivative of y squared with respect to x is going to be 2y times dy dx. The derivative of 1 is 0, and the derivative of x squared is going to be 2x. Next, we want to isolate dy dx, so we're going to divide both sides by 2y. Next, we can reduce this, so we just get x over y. And then we're going to take this point where x is 1 and y is root 2 and plug them in to find our slope. So we get 1 over the square root of 2. Alright, so now that we have our point and we have slope, we're going to plug them into point-slope form to find the equation of the tangent line. So we get y minus root 2 equals 1 over root 2 times the quantity x minus 1. This example says, given that x is equal to t cubed minus 12t and y equals t squared minus 1, we're going to find the first derivative and the second derivative. Then it says for which values of t is the curve concave upward. To find the first derivative, dy dx, it's equal to dy dt over dx dt. In the numerator, we take the derivative of y with respect to t. So right here, the derivative is going to be 2t. And then in the denominator, we take the derivative of x with respect to t. So the derivative is going to be 3t squared minus 12. So there's our first derivative, dy dx. Next, we're going to find the second derivative. So according to the formula, we're going to take the derivative of the first derivative, and then we divide that by dx dt. So again, in the numerator, we're going to take the derivative of this 2t over 3t squared minus 12, and then we divide by dx dt. So we're going to take this 3t squared minus 12 and write it down here. So now we take the derivative of this fraction, so we're going to use the quotient rule. So according to the quotient rule, we're going to go low and then d high. And the derivative of the top is 2, and then we go minus high, and then d low, so the derivative of the bottom is 6t, and then it's all over the low squared. Next, we're going to take this 2 and distribute it right here, and then we're going to multiply this negative by 2t and 6t. So this numerator becomes this, and then we still have divide by this quantity squared, which is then divided by the same expression. So if we're dividing by the same expression, you can think of this as quantity to the power of 1. And dividing by this is the same as multiplying by its reciprocal. So it ends up being that you have this quantity squared times the same quantity to the power of 1, which makes the total quantity to the power of 3. Next, we're going to combine like terms in the numerator. And then we're going to simplify this up a little bit. I want to factor out a negative 6 in the numerator. And then inside here, I want to factor out a 3. So in the denominator, I just want to be really careful. We're factoring out 3 from both of these terms. So that leaves us with t squared minus 4. But this expression is still being raised to the power of 3. So now this is going to be 3 cubed, which is 27. So now finally, we can reduce this 6 and 27. So for the second derivative, we get this fraction. Next, the problem wants us to find for which values of t is the curve concave up. So again, to be concave up, the second derivative needs to be positive. So we want to figure out for which t values will this fraction be positive. So I want to look at the numerator first. In the numerator, we have t squared plus 4. No matter what value you plug in for t, this is always going to be positive, and then a positive times a negative is going to be a negative. So the numerator will always be negative. That means in order for this fraction to be positive, this expression right here would need to be negative because a negative divided by a negative would make a positive. So again, in order for this fraction to be positive, that means this expression right here needs to be negative. So we have t squared minus 4 is less than 0. And t squared minus 4 is a parabola that's shifted down 4. It's opening up and it follows the pattern 1, 1, 2, 4. So you can see here's the graph. And looking at this graph, we can see the values over which this equation is negative. That would be where the graph is below the x-axis. So that's between negative 2 and positive 2. So we have t is between negative 2 and positive 2, and that would be the values of t over which the original curve is concave up. This example says, given the parametric equation, find the points on the curve where the tangent is horizontal or vertical. A tangent is horizontal when dy dt equals 0. So we're going to take the derivative of this equation and set it equal to 0. So the derivative is 6t squared plus 6t, and we set that equal to 0. So I'm going to factor out 6t, and we get 6t times the quantity t plus 1, and we're going to set both of these equal to 0. So you get t equals 0 and negative 1. Next, we're going to take these values for t and make a txy chart. So we have t equals negative 1 and 0. So we take negative 1 and we're going to plug it in for t up here to find our value for x. So negative 1 cubed is negative 1, times 2 makes negative 2. Negative 1 right here squared makes positive 1 times 3, so that's just 3. And then negative 1 times negative 12 is positive 12. So negative 2 plus 3 and positive 12 makes 13. Next, we're going to take t equals 0 and plug it in, and we get 0. And then we'll do this again for y. T is negative 1, so we'll plug it in, and we'll get our y. And you get that y is equal to 2. When we plug in 0 for t, we get y equals 1. So here's our coordinate points. So our points on the curve where the tangent line is horizontal are 13, 2, and also 0, 1. So now we're going to do the same thing for where the tangent line is vertical. So the tangent is vertical when dx dt equals 0. So we're going to take the derivative of this and set it equal to 0. So for dx dt, we get 6t squared plus 6t minus 12, and we set this equal to 0. I factored out 6, and we're left with t squared plus t minus 2. Next, I'm going to divide 6 from both sides of the equation. And then we can factor this to t plus 2 times t minus 1. So we end up getting that t is equal to negative 2 and 1. So now we're going to set up our txy chart. All right, so we're going to plug in negative 2 for t right here to solve for x, and you end up getting 20. Next, we're going to take 1 and plug it in for t to solve for x, and you get negative 7. We're going to do the same thing for y. We're going to plug in negative 2 for t right here to get y. And then last, we're going to plug in 1 for t here to get y. So the points on the curve where the tangent line is vertical are 20, negative 3, and negative 7, 6. For this example, we're given x equals 1/3 t cubed, y equals 1/2 t squared, and then we have that t is between 0 and 1 inclusive, and it says find the length of the curve over the given interval. So we're going to use our length formula for a parametric curve. We have the integral from alpha to beta, and then we have the square root of dx dt squared plus dy dt squared. So first we're going to find dx dt and dy dt. Right here when we take the derivative, we bring the 3 down, the 3's cancel, and then we get t squared. For dy dt, we bring this 2 down, the 2's cancel, and then we subtract 1, so we get just t to the 1. For our length formula, we take the integral from 0 to 1, and then we have the square root of, and it's going to be dx dt squared plus dy dt squared. All right, so we have this set up, so now we're going to do a little bit of manipulation so that we can eventually take the integral. So here we have t squared squared, so this is going to become t to the 4th. Next, I'm going to factor t squared out of both of these terms. So when you factor t squared out, you're left with t squared plus 1. The square root of t squared is just going to make t. All right, so now what we're going to do is in order to integrate this, we're going to use u substitution, and we're also going to convert the limits. So we're going to let u equal this t squared plus 1. So we have u equals t squared plus 1. We're going to take the derivative of this with respect to t. So we get du dt equals, and then over here, the derivative is 2t. And then we're going to rewrite this so it's dt equals du over 2t. Next, we're going to convert our upper and lower limits. So we're going to take this 1 and plug it in right here. So we get 1 squared plus 1, and you just get 2. And then we're going to take our lower limit 0, and we're going to plug it in. So 0 squared plus 1 is 1. And finally, we're ready to plug all of this into our integral. So we have the integral, and then we're going to go from 1 to 2. Drop down this t. We're going to plug in u right here, so we get the square root of u. And then finally, instead of dt, we're going to write du divided by 2t. And this worked out great because these t's are going to cancel. And then I'm going to bring this 2 to the front as a 1/2, and at the same time, I'm going to rewrite this as u to the 1/2. And we're ready to integrate. The integral of u to the 1/2, we add 1 to the exponent, so we get 3/2, and then we divide by 3/2, which is the same as multiplying by 2/3. And remember, because we converted our upper and lower limits, we don't plug u back in, we just leave them as 1 and 2, and we'll plug those values straight in for u. One more thing, I'm going to bring this 2/3 to the front so that the 2's cancel and you just have 1/3. And then we plug in 2 minus plugging in 1. And then right here, this is 2 to the 3/2. So I'm going to rewrite this as the square root, and then it's going to be 2 cubed. So I'm just going to write that out. Over here, this is just 1. So I'm going to bring over the 1/3. And right here, the square root of 4 is 2. So we get 2 root 2 minus 1. And that's our final answer, the length of the curve from 0 to 1. This example says find the length of the curve given that x is equal to a times the quantity cosine of theta plus theta sine theta, and y equals a times the quantity sine of theta minus theta cosine theta. And then we're given that theta is in between 0 and pi. All right, so the first step to finding the length of the curve is we want to find dx d theta and dy d theta. The first thing I want to point out is that a is a constant, so I'm just going to bring it down. The derivative of cosine is going to be negative sine. And then to take the derivative of this term, it's going to require the product rule. So the derivative of theta is 1, and the derivative of sine is cosine. We start in the upper left corner, we multiply these together, and then we add the product of these guys. So we get theta cosine theta plus sine of theta. And then if you look inside the parentheses, you can see that these sine thetas are going to cancel. So we just get a times theta cosine of theta. Next, we're going to find dy d theta. Again, we're going to take this a value and drop it down because it's a constant. The derivative of sine is cosine. And then right here we have a product of functions. So to take the derivative, we're going to use the product rule. The derivative of negative theta is going to be negative 1. The derivative of cosine is negative sine. And then we start in this upper left corner, we multiply these, so we get positive theta sine theta. And then we add the product of these, so that's negative cosine theta. And this is great because these cosines cancel. So we end up getting a times theta sine theta. We're ready to plug everything into our formula for length. We have the integral from 0 to pi, and then it's the square root of dx d theta, which is this quantity squared, plus dy d theta, this guy, quantity squared. Next, this is kind of cool. You have this a theta times cosine theta, and it's being squared. And then over here you have a theta times sine theta, and that's being squared. So we can actually separate this to a theta squared times cosine squared, and we can do the same over here. And you might be noticing where we're going with this. Both of these terms have a theta squared, so we're going to factor that out. So when you factor a theta squared to the front, you're left with cosine squared theta plus sine squared theta. And this is your Pythagorean trig identity, and this equals 1. So that worked out great because this equals 1. Now we just have a theta squared times 1, or just a theta squared. And then the square root and the square are going to cancel. So we just have the integral of a times theta. And remember, a is a constant, so I'm going to pull it to the front. The integral of theta is 1/2 theta squared. I brought the 1/2 to the front, so now we're going to plug in pi minus plugging in 0. So we end up getting 1/2 a pi squared. Alright guys, thanks so much for watching, and I hope this helped with derivatives and arc length for parametric curves. Please subscribe to my YouTube channel, Math with Yosh, and hit the like button. It looks like someone's super excited to do some calculus. Just kidding, she's just sitting here because I was eating popcorn.